Have you ever wondered what would happen if we could solve our toughest problems not by meticulously designing a solution, but by letting one evolve all on its own? Well, today we're diving headfirst into that exact idea, exploring the incredible world of genetic algorithms.
The secret sauce here is something we see all around us: evolution. The core idea of genetic algorithms is to take the fundamental rules of natural selection, survival of the fittest, and apply them to code. It's about harnessing billions of years of nature's problem-solving genius to tackle some of our most complex computational challenges.
All right, so here's our game plan. We'll kick things off with the big idea, survival of the fittest code. Then we'll get our terms straight with a genetic dictionary. After that, we'll walk through the digital life cycle to see how it all works, put it into practice with an example, and finally, we'll unravel the difference between a genotype and a phenotype. Okay, let's jump right in. Section 1, Survival of the Fittest Code. What does that even mean?
Seriously, just think about that for a second. Instead of a programmer sitting there trying to figure out every single line of code, every single possibility, what if you could just create a digital environment, throw in thousands of random potential solutions, and let them compete, breed, and adapt over generations until the absolute best one rises to the top?
Well, that's exactly what a genetic algorithm does. It mimics evolution to find needles in haystacks. These things are optimization powerhouses, capable of sifting through massive, almost infinite search spaces to find the best possible answer. And this isn't just theoretical stuff. They're used for everything from designing antennas for spacecraft to figuring out the best stock trading strategies.
To really get how this all works, we've got to learn the lingo. It's like we're translating biology into the language of computers. So let's build our genetic dictionary.
First up is population. Now, we're not talking about animals or people here. In our world, a population is simply our initial pool of candidate solutions. Think of it as a big collection of first drafts or rough guesses for how to solve our problem. Now, each single individual solution within that population, we call that a chromosome. It's like one specific creature in the herd. And just like real DNA, it's represented as a string of data that contains all the information about that one particular solution.
And if you zoom in on that chromosome, you find the genes. These are the basic building blocks, the individual pieces of data in that string. Each gene codes for a specific little trait or instruction within the overall solution.
Okay, but how do we know which of these solutions are any good? This is where the most important part comes in, the fitness function. This is our judge and jury. It's a system we design that looks at every single chromosome and gives it a score based on how well it solves the problem. A higher score means it's more fit and more likely to survive.
All right, we have our vocabulary down. Now let's see how all these pieces come together in a process we can think of as a digital life cycle, churning out better and better generations of solutions. It's really just a loop that keeps repeating. We start things off by creating a random population of solutions. Then, we select the best ones to be parents. They create new offspring through processes called crossover and mutation. And finally, this new generation replaces the old one. Then the cycle begins again and again and again, getting progressively better each time. Let's look closer at selection. So, once our fitness function has scored every single solution in the population, it's time to play favorites. The algorithm picks out individuals to become parents, and no surprise here, the ones with the highest fitness scores have a much better chance of being chosen to pass on their successful traits. So once we have our two fittest parents, they get to reproduce through something called crossover. And it's actually really simple and elegant. The algorithm just picks a random spot on both of their data strings, and then it just swaps the ends. So the beginning of parent A gets stuck with the end of parent B, and vice versa. And just like that, you have two brand new children that are a mix of their successful parents' traits. This is the main way good ideas get combined.
But, just combining old ideas isn't enough. You need some genuine novelty, and that's where mutation comes in. It's a tiny, random glitch. A single bit in the data string randomly flips. It might seem like an error, but this little bit of chaos is absolutely vital.
So, why is that random error so critical? Well, because without it, the algorithm could get stuck on a solution that's pretty good, but not the best. Mutation is that spark of random genius, that wild card that allows the algorithm to explore totally new avenues and maintain diversity, preventing the whole population from becoming too similar. Okay, I know this is still a bit abstract, so let's make it real with the classic computer science puzzle called the 8 Queens problem. The goal is simple. Place 8 chess queens on a standard chessboard so that no two queens can attack each other. It's trickier than it sounds.
Take a look at this. Each state here is a chromosome, one possible arrangement of queens. The fitness is our score, which is just the number of pairs of queens that aren't attacking. The top solution, with a score of 24, is the best of this bunch, so it gets the highest chance of being selected as a parent, 31%. Compare that to the dud at the bottom, which only has a 14% chance. You can see evolution in action right here.
All right, one final crucial concept to lock in. We need to understand the difference between the raw code the computer is messing with and the actual real-world solution that code represents.
Think of it like this. The genotype is the raw recipe, the string of ones and zeros, in this case 11000. It's what the algorithm actually manipulates through crossover and mutation. But the phenotype is the cake you bake from that recipe, the actual solution, the number 24. The algorithm works on the recipe, but we judge the quality of the cake.
And that brings us right back to the beginning. We've seen how these incredible algorithms borrow from nature's playbook, using selection, crossover, and mutation to literally evolve solutions from scratch. This approach is already creating designs and solving problems in ways we never could have planned. It makes you wonder, if we can truly harness the power of evolution in our code, are there any problems we can't solve?